Greetings. I welcome you all to the 17th lecture of this course, where we will now be discussing and basically continuing on what we had started in the previous lectures. So, when we started discussing metallurgical waste recycling, uh, and we started going into the metallurgical wastes, we have covered aluminum dross and aluminum slag and the aluminum industry wastes, including red mud. And we were now discussing on copper wastes, and we have covered copper smelter slag, and we were discussing copper raffinate solutions. And now we will continue on our discussion on raffinate solution recycling. And we had seen that in the previous lecture that there are a wide variety of ions that are present, the metal ions, the ions that are present that contribute towards the uh, metallic content as well as the non-metallic content, the sulfates that are present. These ions are basically making the solution hazardous, and the recycling of these solutions is of utmost importance. So, what do we mean by developing a good recycling strategy? We've already discussed that it is important to understand the raw material itself. When we have seen the composition of the raffinate solution, we understood that the metallic content in the raffinate solution can be safely extracted. Similarly, the sulfate ions can also be somehow extracted. Let us now look at some of the important strategies that can be used for recycling the raffinate solutions. Now, before we go there, we would now try to look at some of the environmental impacts that are associated with, let's say, improper disposal of the raffinate solutions. Of course, it is very well understood that industries are oriented, industries have invested on the methods of utilizing the raffinate solutions. But one must also think what actually happens when we are trying to discard, when we try to dispose of these raffinate solutions without any pre-treatment. So, without pre-treatment, without any mitigation methods, if we just release these solutions into the environment, what can happen? So, we know that a variety of ions are present in the solution, and these are some of the metals and metal ions that can be, and of course, this is the sulfate ion that are present in the solution. And we've seen the composition. If this type of composition is present, these metal ions are basically commonly present in the solution, in the raffinate solution, of course. So, we know that a major chunk can be iron and sulfur, and to some extent, since we are actually looking at a copper solution, so we know that copper can also be present to a good amount of extent, iron and sulfate. So, the safe disposal becomes necessary. If it is present, then it's an opportunity to recycle. Good source metallic values. Now, the question comes, is it possible to extract some material from a solution? We already know that the good methods that are present are basically solvent extraction, we have cementation, precipitation, ion exchange, and if at all we would like to include, we can also have crystallization. So in today's class, we are actually looking at raffinate recycling. A similar solution that we will be discussing in the upcoming classes is basically the spent electrolytes. So when we look at spent electrolytes, spent waste electrolytes, and where are these electrolytes coming from? These electrolytes are basically electro-refining wastes. Electro-refining process. So when we know that these types of solutions are present, and of course these electrolytes are also in liquid form, and we know that the raffinate is also in liquid state, the recycling process is pretty much common. Solvent extraction, cementation, ion exchange, precipitation and crystallization, these processes are roughly used one after the other or standalone, and these can be used in both of these types of wastes. And of course, we will be discussing on spent electrolytes, waste electrolytes in the upcoming sessions. Various processes are developed for safe disposal and extraction, because of course we know that it's a good source of metallic values, and disposal of these ions directly into the environment really is hazardous, because we have cadmium, we have iron, we have the sulfate ion itself, and these ions are really hazardous when we are trying to dispose of without actually reducing the concentration of these ions. So safe disposal and extraction is really important. What are the methods of recycling? Recovery of iron from raffinate, as we had just discussed, it's either precipitation, solvent extraction, cementation, ion exchange or crystallization. So methods of recycling obviously would like to include these in one form or the other. So chemical precipitation and basically coupling it with or making it standalone with ion exchange. So if we are making a phase called xerosite, and the iron can be entrapped in the xerosite phase, we have seen that the precipitation becomes lot easier and it generates higher percentage of iron. It's nearly about, it has been reported that nearly around 70% of iron can be recovered by xerosite precipitation. And of course, when we know that the precipitation process is being carried out, temperature and pH are important parameters. So we know that in every step of a recycling process, there are important parameters. There are important parameters that basically govern, that direct the overall efficiency of process. So, and we know that pH and temperature are important parameters here. A range of temperature that has been observed for chemical precipitation of xerosite that entraps iron from the raffinate solution is basically it's around 70 to 95, 95 degrees Celsius, and pH could be of the range of 2 to 3. Now, of course, these ranges can differ, but it is seen that these are important parameters and it helps us in achieving the desired product. And of course, using this precipitate, some other valuable product can be made. So this is not the end. Basically, we would try to recover metallic values from the precipitated phase. Now, the next method that can be understood is basically nanoparticles using the raffinate solution. What type of products are we making depends upon the processes that we are employing, and it is the other way around as well. Many a times we are more oriented towards developing a process for a fixed type of product. So it can be thought in both the ways. We can think of devising a process which can give us some sort of product, or we can go the other way around as well. So for instance, if we have a product in our mind, and then we can basically insert the necessary processes so that we can achieve that type of product. So if we have if we wish to make nanoparticles, so how do we go about with this? Magnetite Fe3O4 nanoparticles using copper raffinate solution. So we take the raffinate solution, we have the reduction stage, where we are basically reducing iron 3 ions to iron 2 ions, the change of valency basically, and then we have the precipitation stage. Which is where we are basically removing aluminium from the solution. Now, one might wonder, do we have large quantities of aluminium in the solution? The answer is no, but it affects the formation of nanoparticles. So if during the process of making nanoparticles, some amount of aluminium is present, then it can affect the whole process itself. So multiple stages are being performed in order to achieve higher efficiency and quality of the finished product. In this case, it is nanoparticles. So magnetite, nanoparticles, Fe3O4 is the required product, and the hindrance that people have found is the presence of aluminum. So one has to avoid that. The necessary step that becomes a part of the process is basically removal of aluminum from the solution itself, so that the formation of nanoparticles becomes easier. And finally, the oxidation stage, where one can use different types of reagents. And finally, we get nanoparticles of Fe3O4. Now let us just understand what exactly is happening. We have the raffinate solution. The first thing that we would like to do is change as many Fe3 plus ions to Fe2 plus ions. So this is basically reducing stage. We are trying to convert Fe3 plus ions to Fe2 plus ions, because of course the oxidation stage has its own set of parameters, pH, temperature, and all the related parameters. So it is necessary to have those ions converted beforehand. After that, we have the precipitation stage. We've already discussed. So after this, we need to remove aluminium because it can cause hindrance. And after that, the actual oxidation is being carried out. So we have Fe2 plus ions which will be converted to Fe3O4. So the last step is basically just oxidation, and during the oxidation the formation of nanoparticles is taking place. So what type of oxidation processes are available? We can use the addition of oxygen, or we can have the addition of H2O2, or one could simply just increase the concentration of Fe3 plus by introducing Fe3 plus type of salts into the system, and this helps in the generation of the nanoparticles that are the required finished products. We will now look at the utilization of raffinate for leaching of low grade ores. What does that mean? It means it is just as simple as it is written. Basically, the raffinate, as we have seen, is a good source of ions and all types of ions. So it can have negative ions as well as positive ions, anions and cations, negative and positive. So we have both types of ions present in the raffinate solution. It's a good source of ions, which means it can still react. The ions can assist in the leaching process. And of course, raffinate is in the aqueous medium. So one really just needs to adjust the acidic content. So one can think of adding some more acid into it if it is required. So low grade ores, which can have relatively lesser quantity of let's say copper, because this raffinate solution originated from copper industry. Of course, we know that origin is basically copper industry. So one would really like to use this raffinate solution in leaching of low grade ores of copper itself. Copper ores. So if the concentration of copper in the ores is relatively very less, this raffinate solution can be used as a raw material for leaching these ores, and one would get the metallic content. So again, let us just redraw. We have the raffinate, So we have taken the raffinate and we leached it with low grade copper ores, and what exactly are we doing? We are bringing this raffinate in contact with the low grade ores, allowing it to react with it and tapping out the leach liquor. So of course it will also lead to the generation of the residual solid, and some amount of copper may still be left in the residual solid, but it has been reported that as high as 96% of copper can be leached. So just by using a waste solution that contains the ions, it is possible to extract a really good amount of metallic content from low grade ores. So low grade ores, which are normally used by hydrometallurgical processes. So normally what happens, it is just a common way of understanding that the higher concentration of metallic values, the ores that have these types of metallic values are normally subjected to pyrometallurgical route. And lean ores, if the metallic content is relatively very less, then these can be subjected to hydrometallurgical processes, as these processes really do not require high temperature, and it is the process economics and process speed. So in hydrometallurgical processes, basically the leaching process can be taking up relatively larger time compared to the pyrometallurgical processes. So these are the differences that can be seen in hydrometallurgical processes as well as the pyrometallurgical processes. Normally it is seen that lean ores are subjected to hydrometallurgical processes because the extraction of metallic values from lean ores is relatively more easier in hydrometallurgical processes. And of course, one might want to discuss this, that it is also possible that you can use lean ores in the pyrometallurgical route as well, but the amount of other phases, the other minerals, the gangue minerals that are associated with the lean ores, these are relatively in very large quantities. So one has to invest a lot on the pre-treatment of the ores itself, so that they are made more fitting for the pyrometallurgical process. It becomes a little bit more easier on the hydrometallurgical process. Just the same concept is being used in this process as well. So instead of having a fresh acid solution, fresh leaching reagent, one could just use the raffinate solution, adjust the concentration of the acid as per requirement, and then subject the whole process of leaching. And then what it does is basically it helps in the extraction of metallic values. 96% can be recovered from these low grade ores. Now there is an important other process that we can think of which helps in recovering metallic values and the anions and cations that are present. We will just discuss this in brief. It can be referred to as bipolar membrane electrodialysis. And of course, these processes, some of these processes that are being discussed in the course are being explored on laboratory scales. So one has to be considering the fact that it is a process that can be used on a lab scale, and some of these processes can be scaled up. So bipolar membrane electrodialysis is one of those processes that are being investigated. What we know is that there are membranes and the solutions are inserted in various cells, and then these membranes are helping in extracting the ions in different compartments that can be arranged across these membranes. And of course, we know that such type of membranes, as we had mentioned in the previous lectures also, polymer inclusion membranes, liquid membranes, ionic membranes, ionic liquid membranes. These membranes are basically helping in extracting the required metallic or anionic or cationic, whatever types of ions these are targeting. These ions are captured and transferred to the other solution that is on the other part of the membrane. So, and many a times one has to supply electricity, and at times, since this process is electrodialysis, one has to, well, it is easy to understand that one will be supplying electricity across the solutions. They will have separate electrodes and it will help in the movement of ions. But at times, for instance, in many other inclusion membranes or other membrane processes, one really does not need the electrodes. One really does not need the current to be flowed. It is just the concentration of ions in the solution that helps in basically selectively, the ions are basically removed from the solution and these are selectively picked up and then transferred onto the next solution. So, these types of processes are also present in the current literature that helps us understand that raffinate solutions can also be recycled by not so conventional processes. So, we already know that if one has to tap onto the metallic content and the anionic content, cationic content of the raffinate solution, maybe one can follow the conventional processes: solvent extraction, ion exchange, precipitation. But there are other processes also. The direct utilization of raffinate is one of the common routes that are being employed for good metal recovery. In the upcoming classes, we will be looking at some other wastes of copper industries. Thank you.